flip-flop. See, your memory is actually made up of flip-flops. Combining flip-flops, we get register, and combining registers, we get memory. Memory can be of any type. Right now, I'm not specifying any fixed type. Memory can be of any type. It can be your RAM, it can be your ROM, or it can be your any secondary memory, anything. So this is the scenario. Now, this was the basic of digital electronics. Now, what we are going to do now, coming to our syllabus. If I talk of our syllabus, then as per syllabus, the first thing what we are supposed to learn is register, transfer, and micro operations. Is it fine? Secondly, we are supposed to learn the hardware design of our basic computer. Now, basic computer I am talking of CPU, that is Central Processing Unit. The thirdly, what we'll be discussing as per our syllabus is design of micro program sequencers. Now, don't worry about this term, we'll be discussing later on. Then we need to discuss certain design issues with related to Central Processing Unit. Say I'm discussing the syllabus, huh? Then next, what we will be discussing is pipelining. Sir, what is this pipelining? We had heard the water pipes, drainage pipes. Now in our case, hardware pipelining, the exact concept what water pipes does is applied into our processor. So pipelining. Then you need to understand computer arithmetic. So what is computer arithmetic? Computer arithmetic is nothing but, I tell you, how our addition, subtraction, multiplication, division operations are carried out. That is to be learned in computer arithmetic. Then next, what you are having is input-output organization, because in our system, we need to have some input-output organization. That means because to our computer, input-output devices are attached. So how they work? So that is the last 7th unit. And lastly, we'll be discussing that is memory organization. Memory organization means we are having different types of memory, like we are having cache memory, then RAM, that is primary memory we term. So along with that, we are having ROM. There are certain auxiliary memories also available. So that we will be discussing. So this is your actual syllabus. So we'll be starting up with this unit today, that is the first unit. But before again starting with that unit, what actually our program is. See, you all have studied the block diagram of a computer. You all have studied the block diagram of a computer. This is what we term it to be a CPU. Okay, now this CPU is again, just a minute. This CPU is consist of three parts. One is we term it to be ALU, second CU, and third memory. That is primary memory. Now this completely we term it to be CPU. Then we are having input which is given to CPU, and we get the output which we term it to be output device. So we give some input right now. See, I'm giving some inputs. I'm typing over here. I'm writing on my digital pad. So it is my input to the system, which is given to CPU. It processes and it displays onto the output. So input is my digital pad and output is mine as well as your monitor or display device. But whatever I give input is processed within this unit, and this unit contains of ALU, CU and memory. Now this ALU control unit and memory, the design of this CPU we are going to learn during our curriculum. That means how ALU is designed, how control unit is designed, and memory, how it is designed, that you are knowing. But how it can be further attached to our system, that is what we are going to learn. I hope I am clear to you all. Is it fine,
Yes,
everyone?
sir.
Please don't hesitate in asking the doubts, huh? Please. See, let us recollect it from start. We started up with digital electronics. So the digital electronics part, then we went to sequential circuits, then we went to our syllabus, then we started up with the block diagram of computer, and in our syllabus, this is we want to learn. That's it. So in your CPU subject, you started up with a block diagram of a computer, and now you are moving or you are going into a detail of that block diagram. Okay, so let's start with the first unit of our syllabus, that is register transfer and micro operations. So how to start with that? Let's start with that. Now I'm switching to the presentation area. So this is our first unit, that is computer data representation and register transfer and micro operations. Just a minute, friends. Okay, fine. So we are starting with our part, that is the first unit of the syllabus, that is computer data representation and register transfer and micro operations. So starting up with the first part, what is register? Is already discussed. Register is a combination of flip-flops or group of flip-flops combined together. As I discussed an example of 4 flip-flops only. I combined 4 flip-flops. Now if I combine 8 flip-flops, then it would be a 8-bit register. If I combine 16 flip-flops, then it would be a 16-bit register. Just a minute, friends. Yes, sorry friends, let's continue further. Yes. So register. Now, as discussed, register is a group of flip-flops. So let us now go into the detail of it. So computer registers are designated by capital letters. See, now we are giving the name to the registers. We want to give the name to the registers. So how it can be given? Likewise, say register R1. This is a register. Sir, what is the size of this register? I'll come to this later. We can give the size 4-bit, 8-bit, 16-bit, whatever we want to. See, you also in computers right now you are having 64-bit OS, 32-bit OS. What is that actually? 32-bit OS means register size is 32 bits. 64-bit OS means 64-bit size register is supported. That's right. So 32-bit register, 16-bit register, any size register you can take. So for example, we can have memory address register, we can have program counter as a register, we can have instruction register, we can have processor register. Don't worry about this, we'll come to this in detail. These registers, memory address register, program counter, all this we are going to study in detail. But just for the sake of an example, I am putting that MAR stands for memory address register, PC stands for program counter, IR stands for instruction register. In R1, I'm saying it to be a processor register. Over here, I can say R1, I can say R2, anything I can say. And any number of registers I can take. So this is my register R1. Same way, I am showing the individual bits of register. See, 0th bit. Now always remember the bit counting starts with 0. The bit counting starts with 0. 0th bit, 1st bit, 2nd bit, 3rd bit, 4th bit, 5th bit, 6th bit, 7th bit. But total 8 bits. Then we are having another register. I am taking it to be R2. But the numbering of these bits, I am giving it from this side. See, from your right side, 0th bit and last bit, 15th bit. So this is a register of size 16 bits. I'll ask you the question, don't worry. I'll ask you later on what size of register it is because it is required. We should have the size of register to be fixed into our computer. Then again, I can divide this register into two parts. Say for example, I can say 0 to 7 bits, which is lower bits. L stands for lower bits and H stands for higher order bits, that is 8 to 15. So these are the different representations of a register. Register R1, then I can show individual bits of registers. Then I can simply show the numbering of the bits. And I can also divide the register into two parts. That is lower half and higher half. That means lower order bits and higher order bits. Is it fine, everyone? Okay. So register, we are now moving on to the detailing of the hardware. That is, we started up with register. So now, if I move further, the question arises, what is micro operation? See, my chapter unit name is only that thing. See, register transfer and micro operations. So what is now micro operation? See, I started up with register. We are clear with register now. Then moving on to the next definition, that is micro operation. Now learn the term micro operation. The operations executed on data stored in registers are termed as micro operations. See, you all have studied C language, you all have studied C++ language, wherein you are using operators, like let's say plus operator, minus operator, but that operators you are applying on data. But over here, micro operations we are talking. The micro operations are the operations which gets carried out onto the data stored in registers. See, the word important is registers. Is it fine? Then again, I can say a micro operation is an elementary operation. See, it is working or any operation is getting carried out at register level, means it is carried out at microprocessor level. So it is microprocessor, not operating system. So it is carried out at microprocessor level. That's why it is termed as an elementary operation performed on the information stored in one or more registers. Say for example, I am giving some input. Let's say I am writing hello. See, I am writing hello means I have written hello into my digital pad. It got transformed to digital form. Digital form means I am talking, it got transformed to binary data, 0 and 1 signals. And this digital data is sent to my processor. This processor contains some registers. See, processor contains registers, and that data is processed at processor level, and then we are getting this data onto our display. That means our screen. Can you see this? So this is how the role of registers comes into the picture. And along with that, there are certain micro operations carried out onto the registers, like data transfer. Then it can be logical operation, it can be arithmetic operation, it can be shift operation. Anything can be carried out onto this data, on this binary data. So micro operation is an elementary operation performed on the information stored in one or more registers. And again, see, I have performed micro operation. The result of operation may replace the previous binary information. Say for example, I am having this register. Let's say a 4-bit register wherein I have stored the data 1010. This is my data. Now some operation is carried out onto this, and this data may or may not, see, it is not compulsory, may or may not get replaced. Say for example, I have applied some operation, I'd say performed addition, and my result comes out to be, let's say, just a minute. Say after performing addition, it comes out to be, let's say 11110. See, the data got replaced. Or it may also happen that from this register I transfer the data to another register. Like let's say I transferred it over here. So this is my 1110. So what the statement says, the result of the operation may replace the previous binary information of a register or may be transferred to another register. So micro operations are operations carried out onto the data stored in registers. It's very simple. So example can be shift operation, can be count operation, can be clear operation. That means, say for example, I want to clear the registers. Now clearing the registers, I want to clear this data. So I cleared the registers. Same way I can load the registers. Load means I can write it. Load means I want to load it. Let's say 0001. So these are the examples I had stated, that is shift, count, clear, and load. So now the next terms comes is, see, we had studied two terms. The first term was register, second term micro operation, and now third term comes into the picture, that is register transfer language. See, you are having two registers. Let's say register 1 R1 and let's say register R2. What the term is? Register transfer. Register transfer language. Language. Sir, is it like our normal routine language, C language, C++ language? No, right now I'm not saying that. Just the notations will be there. Few notations will be there. Fine. So let us define the register transfer language. Symbolic notation used to describe the micro operation transfers. Read the definition carefully. Symbolic notation. See, what is register transfer language? It is a symbolic notation. It is a symbolic notation used to describe micro operation carried out among registers. That's why it is termed as register transfer language. So now the question is, we need to learn the symbolic notations. Again, the term register transfer implies the availability of hardware logic circuits that can perform a stated micro operation and transfer the result of operation to same or another register. See over here, the textbook, what has been mentioning is saying you the something what is already discussed previously. Register transfer language is a system for expressing in symbolic form. See, the same statement. This statement I copied it from the textbook intentionally. See, the symbolic notation used to describe micro operation transfers. Over here, the register transfer language is system for expressing symbolic form, symbolic notation. Form the micro operation sequences among the registers of a digital module. Yes, it is obviously a digital module, because registers are always digital circuits. Fine. So moving further, now we are going into the detail of register transfer. So information transfer from one register to another register in symbolic notation is termed as register transfer. Now for this, we require one operator named as replacement operator. Oh, sir, this is a new operator. Anything new? No, it is nothing new. Let's say this is a statement. See, understand the statement. R2, arrow, R1. Now, the direction of arrow is on the left side. What does this indicate? The data from R1 is to be transferred to R2. See, repeating my point again. Copying the content of R1 to R2. See, I am repeating the word copying the content from R1 to R2. It is also termed as, I am saying it to be copying or transferring. Both are same. Please remember, both are same. Copying as well as transferring. So what does this notation indicates? The content of R1 will be transferred or copied to R2. That's why the information transferred from one register to another is designated in symbolic form by means of a replacement operator. And now I am defining this arrow which is written is termed as replacement operator. Is it fine? Is it fine? So this arrow is a replacement operator. So don't get confused. It is not a complex term. It's very simple term. Arrow is replacement operator. Already mentioned, denotes a transfer of content of register R1 into register R2. So let's take an example. See, I am having register R1. I want to transfer the content to R2. So how it will take place? See, this is register R2. It is empty right now. Consider it to be empty. Now I want to transfer the content of R1 to R2. How I would be doing? It's obviously bit by bit. It will be bit by bit transfer. So see, the transfer is carried out. So this is what is register transfer. Sir, you are saying it to be register as transfer. Can we not say it to be a copying a register? Yes, we can say. But technically they had given the term to be register transfer. Is it fine, everyone?
Yes, sir.
Should I move further?
Yes, sir.
Okay, fine. So register transfer. See, now we started up with register, then micro operation, then register transfer language. Now we studied register transfer. So can I say we have introduced one notation named as R2, R1. See, now I would be speaking R2 arrow R1. See, now my convention of speaking would be R2 arrow R1, means content of R1 will be transferred to register R2. Fine. So the first notation came into the picture to us, that is arrow, replacement operator R2 arrow R1. Now see, if I talk of a computer, can I say it is something similar to our human brain? So we never work until unless we give some command at a specific time. See, when we started, can I say our lecture timing was 11:15? So at 11:15, what you people did, you started up with Google Meet, you joined the Google Meet, and I started up with the lecture at 11:15. So a command was given to us at a specific time. A command was given to us at a specific time. That means at 11:15, you are supposed to start the lecture. So time was given to me. A time was given to me to start the lecture. So same way over here, we require some time. Say for example, I want to transfer the content of R1 to R2. At what time? At some time t. Are you getting it? I want to transfer the content of R1 to R2 at some time t, not at any time. There should be some defined specific time. So at time t, I want to transfer the content of R1 to R2. So that is our next point. Register transfer with control function. There should be controlling time. So normally we want the transfer to occur only under a predetermined control condition, that is timing, using if-then statement. So if P is 1, see, now condition came into picture. If P equals to 1, then perform the transfer. Then how to denote this statement symbolically? Where we term P to be control signal. Control signal means at time. Now this value would be either 0 or 1. Huh? The value of P will be either 0 or 1, nothing else, because it is binary. The value of P will be 0 or 1 because it is a binary, it is a Boolean function. This P is a Boolean part. So value will be 0 or 1. So P is a controlling signal generated by the control section. See over here, word use this control section. Into next chapter, we will be using the term control unit. Actually, this timing will be given by control unit. That at this time you are supposed to perform this operation, at this time you are supposed to perform this operation. So that timing is nothing but a binary command 0 or 1. So a control function, what is control function now? A control function is a Boolean variable that is equals to 1 or 0, as I mentioned over here. P is a control function. The value will be 0 or 1. The control function is included in the statement as follows. See, now new notation came into picture. New notation. So what does this statement means? What does this statement means? At time P, so always the value of P will be 1. When P is 1, then and then perform this task. But if the value of P is 0, then don't do this task. Repeating my point again, when the value of P is 1, at that time perform this transfer. But if the value is 0, then don't do this transfer. That's why it is termed as control function. Is it fine? So let's learn that. I am having R1 and R2 registers. See, understand. We never work without clock. Are you working without clock? No, nobody. Because we always have a clock to work on. Say 11:15 was our timing into the clock, that at 11:15 I am supposed to join COA lecture. At 9 o'clock I am supposed to join the workshop. So over here, the same thing occurs. Our register transfer or anything or any of the device do not work without clock. A clock is a very important control in our system. We'll discuss that, don't worry. Now there comes control circuit. See, as mentioned into the system, P is a control signal generated in the control section. So this is my control circuit which will generate my P. Now P means the value of P will be 1. If and only if P will be 1, at that time I am giving the command to R2 register. See, I am giving the command to R2 register that load yourself. Repeating my point again. At time P, that means when the value of P is 1, at that time the command is given to register R2 that load yourself, because over here it is a loading signal to register. So load yourself from where? From R1. Now what does this N indicate? N number of bits. N indicates N number of bits. So how it works? Control circuit give the command P, whose value will be 1. If it will be 0, then loading operation will not take place. Repeating my point again. If the value of P is 0, then loading operation will not take place. Over here it should be 1. Signal over here should be 1 compulsorily. So over here the P will be always 1, which loads the register R2 from where? From which it is connected. So which is R1. Is it fine? And how many number of bits? N number of bits. Now again, sir, what is this clock? Now clock is nothing but it is used for synchronizing our devices. So repeating my point again, clock is used for synchronizing our devices. See, we all are working in synchronization at 11:15 to join the lecture. Repeating the statement again. We are synchronizing ourselves at 11:15 to join the lecture. So we are working on clock. Same way, all these devices which are there into our system, they work on clock. Is it fine? So how it works now? See, this is a clock signal. This is a clock signal. I don't know whether you have studied in digital electronics or not. It is a digital signal, 0, 1, 0, 1. See, this is 0, this is 1. So digital clock. A clock is there which works uniformly. Now when the load becomes 1, see, now when the load becomes 1 at some time t, see this, when load becomes 1 over here at some time t, it became 1 till time t plus 1, till time t plus 1. See, a clock cycle started at this point, it completed its complete cycle. So at time t plus 1, this load will go to 0. Again, this load, these two are separate. The load signal will go from high to low, and at that point of time, see, load signal which was 1 over here, see, it became 1. What should happen? The transfer from R1 to R2 takes place. Repeating my point again, when P value is 1, which is given to load signal of R2, at that time the content of R1 should be transferred to R2. But exactly at what time? Over here, see, over here it became 1. So should data transfer from R1 to R2? No, not at this point. When it became 1? No, not at this point. But when it goes from 1 to 0, see, when it goes from 1 to 0, at that time transfer should take place. At that time, transfer from R1 to R2 should take place. So this is what is actually the register transfer with control function. So quickly revising it again, I want to transfer the content of R1 to R2 at some time t, and the value of P should be 1. So if P equals to 1, then R2 arrow R1. So it is denoted in symbolic notation as P colon R2 replacement operator, that is arrow R1. Digitally, how it take place? Control circuit sends signal 1 at time t. See, at time t, control signal sent P, which is value is 1. So it comes over here at time t. So what happens? Value of P becomes 1. So value of P becomes 1 at this point. It remained 1 till time t plus 1, next clock cycle. And then when it goes to 0 back, when it goes to 0 back, that means when this P is now becoming 0 from 1. Initially it was 1, now it goes to 0 back. So at that time, when it goes to 0, the transfer should occur. A transfer should occur means the content of R1 should be transferred to R2. Am I clear, everyone? All of you?
Yes.
Okay. So
Yes, sir.
I want to stop over here. So today we stop here. Next time we'll be moving further into a lecture. Fine. So that's it. But just you all people put your enrollment numbers into the chat box for your attendance. I'm stopping my sharing. Yes, please put your roll numbers into the chat box so that I can feel your attendance. And that's it for today. We stop here. Thank you, all of you. Yeah, oh, sir. Yes, Ayushi. You are having anything doubt? Ayushi?
Yes, sir.
Yes, please. Yes, please.
Sir, in my timetable, different lectures are there. In my Google Calendar, different are there.
Okay, I'll you are in TC1, no?
No, TC2.
TC2. Okay, I'll check out when I'll contact with your CC. She will guide you in this case.
Okay. Thank you,
Okay.
sir.
Hello, sir. Hello, sir.